We are going to start working on torque with more than one rotational object. And this is going to help us build into inertia and angular momentum. And there's a couple important pieces that go with questions like this. And part of it is that we know that we define torque as being the cross product between force and the distance away that force is exerted. What this does is pull out the perpendicular component of that force. And so we've looked at it and we see this. We see this right here, and we know that that is 90 degrees. So if I turn this into my cross product, I end up with torque is F times the radius, the distance away that force is applied, times sine of theta. And so for the boards and whatnot that we've done, where we have just like this board on some sort of rest, what we've been doing is like hanging something off of that and asking what the torque is on it. And what I keep emphasizing to everybody is that this thing here, the reason why we don't write in the sine theta is because this is a 90-degree angle, right? So if this thing is going to rotate this way, we look at that and we're like, okay, that's 90-degree angle. We don't need to worry about it. And then we did like cables, and we looked at the angle there on our cables, and we were coming up with the tension and then the torque those cables were exerting. Well, for whatever reason, when we turn this now into circles, it gets a little visually confusing. So let's talk our way through it. I know that force 1 is 90 degrees. Let's see, what else do I know? I'm exerting a force going this way. So I'm going to get a counterclockwise rotation. And so this torque here would be positive. This is a positive torque. Now let's look at F2. Now I look at that. That force is going to make it rotate clockwise. Oops, I'm doing it with my left hand, sorry. Oops. Clockwise. So my thumb is going into the page. This is a negative torque. Cool. Now we're given a few things. We know that this radius here is 0.30 meters. And this radius here is going to be then 0.50 meters. And we know that this force here is 50 newtons. And this force here is 50 newtons. And then we're given that it's 30 degrees above the horizontal. So 30 degrees above here. And what we might be tempted to do is to look at this and say, okay, so my torque is going to be this for F2. So torque 2. I'd be tempted to be like, okay, so that's just going to be the force is 50 newtons times that distance away, 0.5 meters, times sine of 30. And then we would be very sad to find out that this is wrong. Let's look at why. We know that this torque here is 90 degrees. I can see that. So one of the ways I can kind of visualize it is I'm looking at, let me just draw this out more, 90 degrees from this extended radius arm, if you will. So kind of draw that out further. So force 1, if I were to make this a force, is acting like this. There's my 90 degrees. So as it turns out, when I look at this piece here, it's not 30 degrees. It is 30 degrees from the horizontal, but it's going to be 90 minus 30 from this radius. So the axis of rotation. So this will be 60 degrees. And that's probably the trickiest part in all of this. And so what I always suggest is go back to what you're comfortable with, right? If I go back to my board and I see this thing acting, this force acting straight down or straight up, how am I measuring that 90 degrees? And let that guide you to all of your other angles that you're going to determine. So for this one then, we have our torques. So the sum of my torques, let's see, we'll go Clockwise equals counterclockwise. So this is going to give me a clockwise rotation. This will give me a counterclockwise. So I'll end up with 50 newtons times my 0.5 meters away that force is being applied from the axis of rotation times sine of 60. Let's see, and that's going to equal this 50 newtons. Oh, actually, we don't know if it's going to equal that. Sorry, we're not doing equilibrium. So let's do our sines. 50 sine, we said that this is a negative torque. Then plus my 50 times 0.3 meters. Yep, and then sine 90. I'll go ahead and write that in there. So what do we get? And I get that the torque is negative 6.7 Newton meters. Now, let's look at something that your book brings up, this concept of a moment arm and the line of action. And so I'm going to use this torque that's at an angle, so it makes a little bit of sense as to what we're doing. The line of action is where that force is being applied. So just kind of trying to draw a straight line, kind of coming out of it. And I can go both ways, right? So this here represents my line of action. The moment arm is the smallest distance from the pivot point, so the axis of rotation, which is right here, to the line of action. So I can draw a straight line. The shortest distance between 2 points is a straight line, so perpendicular to, whoa, magic just happened. I didn't plan for that. There we go. Shortest distance is this perpendicular line. I can kind of draw like that-ish. There we go. Now let's take a look at the angles here. What do I have? I have a bisecting line here. So that is 60. That makes this 60. Makes this 30. And then this is 90. This is my moment arm. So one of the ways that you can look at torque, that you'll see it defined, is that torque is the product of the moment arm, times the applied force, times the force. Whoops. There we go. So the moment arm, how can we look at this? The moment arm is what? It's going to be, this is my radius, and this would be like my right angle. So I want to pull out the moment arm. So I can look at this and say, okay, this is my hypotenuse. What do I have? I have sine of 60 equals opposite equals my moment arm over my hypotenuse. And my hypotenuse is the radius of this circle, so over r. So my moment arm is going to equal r sine theta. Oh, look at this. So this is exactly the same. So I'll have r is that 0.5 meters, and here's my 0.5, and sine theta is sine 60. So there we have it. That's another way for you to kind of make sure that you have the correct angle when you're doing your torques. So it gets you the exact same thing. It's just a slightly different way of looking at it. So I'm going to stop this one here, and the next thing I'm going to go into is the acceleration of this thing.